Hello and good afternoon. Now we're gonna start with our next webinar, which is entitled AI Applied to Artificial Vision for Quality Inspection in the Industrial Domain, Technologies, Examples and Insights, being offered by our ZDZW colleagues from VideoSystems, Matteo and Mattia. So, Mattia, floor is yours.
Good afternoon and welcome. This webinar was supposed to be introduced by my colleague Mauro Fabrizioli, but unfortunately he is unwell and won't be able to join us. My name is Matteo Anese, and I'm working as a data scientist, AI model developer, and AI tools developer in VideoSystems. And this is my colleague.
Good afternoon to everyone. Matteo Di Giusto in VideoSystems. I'm machine vision, machine learning engineer. Sorry for the echo. Okay.
Okay. Probably there are because
maybe you can try to use your microphone, Matteo.
Okay.
Can you hear me?
Yep, we do.
Okay. I'm Matteo Di Giusto, and I'm a colleague of Matteo. And in VideoSystems, I'm a MLOps and vision engineer. And my aim is to develop, optimize, and maintain neural networks model in production. So in our systems, my aim is that to maintain the models.
So this is the summary of today's webinar. And before a small introduction to the project and our company, ZDZW is part of the Twin Green and Digital Transition Calls, 36 months project with 11 million euros of budget and involving 27 partners, including 12 industrial, small and medium enterprises. And VideoSystems, our company, is one of these. The main goal is to offer a non-destructive inspection suite to extend the quality control methods towards higher sustainability, so reducing defects and waste in industrial processes. Destructive tests, in fact, have some troubles. First, they generate waste, and second, they are often manual or at least not fully automated and offline. And third, they will work with the principle of sampling, and so they don't inspect the 100% of the lot. This means that when non-conformity are found, the file production lot needs to rechecking or discard, and thus more waste and inefficiency are created. So on the other hand, non-destructive techniques have some cons, like limitation in costs and integration. And ZDZW has the objective to mitigate or solve some of this. This is the overall picture of the project objectives and guidelines. The aim is to develop a digital non-destructive inspection service or services as a set of strategic technologies to improve production efficiency, zero defect, and sustainable manufacturing of European industries. Six pilot projects stem from different industrial sectors: injection molding, thermoforming, and turbine tower welding and painting, induction hardening, lithography, and packaging. They are planned to validate digital non-destructive technologies coming from three different areas of application, namely the structural integrity control, visual inspection systems, and thermal process inspection. They all target sustainable manufacturing. Our artificial vision technologies, enhanced with artificial intelligence, are part of the visual inspection suite and are tested in the 6th pilot to detect the defects during coffee capsule assembling and packaging in the Ili Cafe plant. And about our company, founded in 1993 and located in northeastern Italy, VideoSystems is a technological provider delivering a vision inspection solution for various industries on a global scale, with hundreds of different projects developed and 7,500 worldwide developed systems. Under different brand names, it specializes in vertical markets by integrating AI-based vision, data, and robotic technologies. VideoSystems addresses quality control challenges, ultimately enhancing industrial competitiveness and contributing to a more intelligent and sustainable society. And despite being a small-size company, VideoSystems is very proud of its engagement in the EU-funded projects. This engagement began nearly a decade ago, going through 3 big consortia projects under the Horizon 2020 program. And additionally, the company has contributed to smaller projects funded through cascade funding calls. Currently, VideoSystems continues its participation with 2 ongoing projects within the Horizon Europe program, including the ZDZW project. What is the traditional computer vision approach? With the expansion of digital photography and its widespread availability, many industries has begun to use cameras instead of the operator's eye, automating tedious inspection tasks and outperform humans in non-destructive inspection tasks. Some use cases are dimensional analysis, spectral analysis, defect detection, pattern matching, and I'm probably missing many others because of the vastity of the things you can do with it. For example, here you can see a result of a dimensional analysis on washers done with classical algorithms, not involving artificial intelligence. It is a simple but effective and fast way to check measurement of parts in the production line. And this is another part of a bigger project involving AI, but this is the part with no AI involved. Is the detection of letters due to difference they have with the background. The feature dimensions are very relevant in this case, and the algorithm is based on them, so they are parameters of the algorithm. So how we can make a project of computer vision, traditional computer vision, so without the AI? We have to build the image acquisition process and the environment in which the images are taken. The more consistent it is, the better it is. Then recursively, through analysis of the images has to be made for developing the software. And in the end, the parameters are tuned to optimize the workflow and the output of the inspection. This type of process is based on the study of the images. So our data and the rules that are established before the traditional computer vision algorithm is developed and deployed. This can be used to get the answers. So if the part has defects or not. This process has some advantages and disadvantages. So the first is more predictable outputs, since the whole software is programmed on a custom data and within known conditions. A small quantity of images are needed to develop the software. More restricted are the conditions, better it is. There is a full control on the solution with less and more effective parameters because are coded in the project. And the algorithm may be adapted if the imaging condition change slightly, because the adaptation is very dependent of the acquisition condition. And they have faster execution times because they don't have to be put under a GPU continuously. And bugs are very unlikely to be found in the most used libraries and tools because they have been developing for several decades now. And the most evident disadvantages of this project of traditional computer vision approach, they are the software may lack flexibility when integrating a new class of defects. So if you have to analyze a new piece, you are not 100% sure you can integrate it in your software. And tweaking the software parameters often require very technical knowledge of the algorithm. So you have to be very skilled in maintaining it. And they are highly susceptible to imaging conditions, which must be controlled and calibrated. Instead, let's see how an AI-enhanced computer vision approach is made. Usually, there is an acquisition of a conspicuous number of images. They are acquired and they are annotated and classified. Then the model can be chosen, trained, validated, and refined. And this is an iterative process, so it can be done better, and always better. And unlike the traditional approach, this process directly feeds answers to the model alongside the data, enabling it to learn the underlying rules. So the rules are the product of the project based on an AI-enhanced model. Let's delve into the process furthermore. This is a defined scheme of typical workflow for developing an AI-enhanced non-destructive inspection system. So we start from the camera acquisition, and then we have to label the images that the cameras shoot. So the labeling can be done in several ways. The first is the manual one. So here you can see a screenshot on the left, or on the left, yes. You can see figures being labeled by a manual operation. And here we have to do practically an OCR, so an optical recognition of characters. This manual operation can be, if applicable, can be automated with traditional computer vision algorithms if they are present in the company, for example. Also, we can use pre-trained model to label the images because maybe we have developed a model before, or alternatively we can use a generic model to try to label the things. So here is an example of a segment anything model that is integrated in our tool in development. And you can see, you can find the background, the glass capsule, and the defect that is present. And alternatively, you can manually hint the model to recognize the particular thing you want to detect. The common annotation types in non-destructive inspection include bounding boxes, so enclosing the defect or object of interest. Segmentation, so as you can see on the left, the pixel by pixel individuation of defects, and the classification, so assigning each image a predefined category. Regardless of the application, the aim is to reduce every doubt of an images. So a human check is very recommended to reduce the error that can be injected in the model. So we have done the labeling process, and after it, we must divide the dataset, the whole dataset, in three groups: the train, the validation, and the test datasets. These subsets serve specific purposes during model development. The training set will be used by the model to learn underlying patterns for the data and minimizing a penalty function. And the validation set is used during the training process to evaluate the model performance while it is iterating the learning process. And validation images have to be associated with a set of suitable metrics and determining so when the training must stop. And lastly, the third set is the test dataset. It remains separate from the training phase and provides an independent evaluation of the model accuracy. The goal is ensuring that the model generalizes well to unseen data. So let's go straight into the model development. And here you can see a plot extracted for our training tool. You can see the loss function that is in blue and the metrics in orange. Of course, every batch of data will result in different values of the function. So you have to do the interpolation by eye now. We can see the loss function is decreasing practically immediately. So the model is learning. And the metrics function in orange reach a peak around 120, more or less. Then we can say the model has reached the most precise solution it could be learned. So then the values of the metric are chosen, and then they descend, suggesting the model is learning too much by heart the samples it is seeing. And this condition is called overfitting, and it should be avoided. So we will choose for our application the model at the peak of the orange metrics function. Then we can optimize it, and now I pass the microphone to Mattia, and let's continue with the presentation.
Okay, so I will talk about more the optimization part of the models, because as Matteo said, the first step you have to obtain a model that is usable in sense of accuracy. But when you are going to deploy the model, you have also to have the performance in terms of inference time. So when you speak about optimization, you could optimize the inference time or the accuracy of the model. When you have to reduce the inference time, you have these cases, these opportunities to do that. So you have the quantization, where you are going to change the representation, the implementation of the weights that are defined inside the network. Usually, weights of the networks are expressed like a floating point 32 number, but you can also decide to use a floating point 16 implementation, having how can I say, having a lighter inference speed. You can also try to represent the numbers in int8, but in this case you have to do further calibrations to have a usable model. int8 is used mainly in on edge devices, so like I don't know, NVIDIA Jetson or devices like that. In pruning, you have to delete. I'm going to say delete some parameters that are useless to the network. Generally speaking, this is done removing some nodes of the network, and practically speaking, you go to put to zero some weights of the network, and you see how the network behaves without these nodes. You can also reduce the size of the image in terms of resolution of the image. So you can, for example, pass from a full HD image to a HD image. But in this case, you have to be you have to pay attention to avoid to loss information, because if you are going to, if you work with I don't know, defects or something like that that is small in terms of pixels, if you downsample the image, there's the risk that the information is lost. So you have to, it's a trade-off between accuracy and inference time. Another opportunity is to change the image format. So for example, networks can be trained on JPEG images or BMP images or PNG images, but you have to be conscious of what the process of compressing the image, because BMP is something like a raw image. So you have a full quality image, but you have an image that is heavy in terms of disk space. While with JPEG you have a less heavy image, but you have less information. Speaking about the accuracy, if you want to improve the accuracy of your neural network, you have these three possibilities. So you can or balance the data sets. So you have to acquire new images and try to have a, how can I say, try to try to balance, okay, try to balance the classes of defects that you have on your data set, because if you have more samples of a class inside the data set, maybe the network will behave with a sufficient accuracy, but it's a bias accuracy, because the training process gives gives more importance to the defect with more samples. So this is not what we want. Ideally, you should have a data set where every kind of defect has the same cardinality inside the images. If also with integrating some new images, integrating some rebalancing in data set and so on, the model can't provide the performance that the user wants, you can also opt to change the model, use a more complex model, or change the internal architecture of the model. You can make a model deeper, adding, for example, some convolutional layers or something like this, and try to test try to retrain the model and see if the accuracy is greater than before. Keep in mind that deeper architectures generally are slower than the little architecture. So it's also in this case is a trade-off. Advantages of this or disadvantages of this approach. I mean, the advantages are related to what Matteo said before. So generally speaking, the neural network approach is more flexible and more adaptable to different acquisition conditions, because by default, during the training, two images are transformed with how can I say, with
continuity. Okay, continuity.
Are transformed with some transformations like brightness, contrast, and geometric transformations. So the idea is to synthetically generate all the conditions that can be present in on the deployment side. In this case, the augmentation, you can also define what are the kind of transformations that are more suitable to the use case. These transformations are commonly known as augmentation. Another advantage is that in production you have less parameters to guide the network behavior. So in general, regarding it depends on the task, but you will always have less than 2 or 3 parameters, because I mean the most important parameter is the confidence. So it's the probability that the neural network gives you about the the answer that gives about the image that you give in input. So you can say that you can consider as good only the predictions that are that have a confidence score greater than, I don't know, 50% or like this. The last advantage is that you can easily integrate new classes of defects, because you have only two. Only it depends on the defect. You have only to integrate new images. You have to integrate your data set and retrain the model with the new class of defects and see how the performance changes, or if they become better, or you have to adjust them. Regarding the disadvantages, you need a lot of images. So, for example, one of the last architectures that are used recently, for example, the YOLO network, requires at least 1,000 images for class. I think it's an heuristic. It can perform good also with less images, but it depends on the task. In this case, in real scenarios, the acquiring of the images isn't simple, because or you have technical difficulties, so you don't have the devices to acquire the images, or you can't generate the images to acquire. So I don't know, speaking about anomaly detection, it's difficult to say to the user, we need 1,000 images of a defective piece, defective, I don't know, defective screw, defective something. It's difficult, and this is one of the main how can I say, main disadvantages of these approaches. Another thing is that the training can be complex. So it's not couldn't say, it's not plug and play. So you have to tune some of the hyperparameters that define how the training will behave during the epochs. So, for example, the number of epochs is an hyperparameter, the batch size, so the number of images that you feed into the neural network in the same time to perform optimization, batch normalization, and something like this. The architecture of the network can be an hyperparameter. So what's the size of the convolution that you use? What's the number of convolution layers that you use, and so on. So this can be a very heavy task to perform. There are some heuristics, some approaches that help you to how can I say, to limit the search space of these parameters, but it's a problem that can simply explode combinatorically. So it needs some processing power. So it's an heavy task. And the third point, every model is a black box. So a neural network or works or it doesn't work. It's difficult to explain why it works and why it not works. And it's difficult to parameterize it. So you have only, as I said before, you have only the confidence, but you can't guide the inference with other parameters. So you can do some post processing on the on the detections or on the classification, on all the segmentation, but you aren't able, you are not able to go deeper. I mean, sometimes it's frustrating because maybe the neural network is able to detect, I don't know, a small defect, but a big defect it isn't. So it's sometimes it's disappointing. So you just don't understand why it does this thing and why it doesn't work, or if it works in this way. The fourth point, it needs longer processing times because the process of the inference is you have to it composed by different steps, so you have to transfer the image from the system RAM to the dedicated RAM. You have to do some processing on it, pre-processing, post-processing. So it can be a time-spending task. So if you have the hardware, the required hardware, the dedicated hardware, so the GPUs, where you can parallelize the tasks, and if you want, you can also process more images at the same time. It helps, but it depends also on the requirements, the functional requirements of the system. If you don't have if you don't have time constraints, you can also perform the inference on GPU, but it depends. It depends on the user, on the task, on the use case, and so on. Okay, so now we're going to show you some real examples. So in this case, some applications. This is an application where these are pharmaceutical bottles. So there are, how can I say, bundles of pharmaceutical bottles where the task was to detect the missing ones, for example, in the third image, or to detect some anomalies inside the bottles. So the computer vision task is divided into steps. The first step is to detect the bottles. So in this case, you can do it or in the classical way. So if you know where will the container will be inside the image, you can draw manually a grid. So you can draw manually a grid that splits the image in shells, where every shell contains a bottle. Then the shells are given in input to a classification network that gives you the result and says to you if the bottle is defective or not defective. You can also the first part of the detection phase, the grid creation, can be also done directly on with deep learning models. It's a detection task, so you can pipeline the two networks. So the first network will detect the bottles, and the second one will with the input, with the output of the first network, will do the classification on the image. This one is another case, another use case where the aim of the system is to detect if the joint between two hot slabs is defective or not. For example, in the above image, there's a good, there's an okay billet, and on the bottom there's the defective one, where you can see that there's an evident crack. In this case, the task is a classification. There are, I can say, two different networks, because the analysis is done online. So you have the images that continuously arrive to the system, and you have to analyze also the parts of the billet that aren't the join. So you have a first network that classifies the image as a join or not, and the second network that based on the result of the first neural network, that classifies the join as good or bad. In this case, there is also a mid class, because some joins can be good, some joins can be bad. Sometimes also the user doesn't know if it's good or it's bad, and I mean, this can be another disadvantage of computer vision in general, because sometimes also the client there are some use cases that also the client doesn't know if it's a good, it's a bad, it's a defect, it's not defect. So in this case, we try to resolve the issue by adding a new class that is the middle one. So we have bad, we have good, we have uncertain. This is another case where the system analyzes the text. In this case, we have a multispectral analysis. So on the left, we have an image on the visible spectrum. On the right, an infrared spectrum. On the left, I mean, the images on the left are used to detect the defects that are, how can you say, the external defects of the egg, so dirt, yolk, blood, or if the egg is speckled, or if it's corrugated or something like this, while the image on the right is useful to detect cracks. So in infrared vision, you have the cracks, hits, and leaks are more evident, more visible, because the infrared light can pass through the shell, so the cracks are evident. In this case, this is a complex problem, because we have two neural networks for view. Because in this case, we have two tasks for the same image. So we have a task to detect the egg, and it's done via a segmentation network. So the green ellipse that you see is the result of an inference with a segmentation network. And then the image is processed by a detection network to detect the defects. So on the left, you can see that the egg number 6707 has some dirt on it, while on the right, you see that the egg number 28 has an hit. So you can see that the network is able to detect every kind of defect. This is a tricky problem, because you have also to match the visible view with the infrared view. So you have the phase of inference to have the results, then you have to match the results, to merge the results in a consistent way to have the final result of the egg, to if the egg is good or if the egg is bad or something like that. Okay, this one is similar to the one that you see before with Matteo. In this case, the problem was solved with classification neural network. As you can see, in this case, the position, the position of the letters and of the characters was not known. So you can crop as a pre-process step. You can crop for example, the blue circles. You can crop these areas, and then you can classify them with a neural network. You can do this with a classification network, or there are also some networks done for the OCR. So there are some architectures that are done specific for reading or numbers, letters, phrases, something like that. The blue square is a data matrix. So a data matrix is something like a QR code. And in this case, the problem is resolved with a detection. So a neural network was trained to detect the dots. Then the dots were converted to a data matrix to have the encoded value of the data matrix. Okay. Last application, last use case was about the study and analysis of some snacks that we have here in Italy. This snack is called Nastrina, and the task was to, in this case, was to classify the snack. So you can, for example, the two first samples, you have OK 100%. And this was a classification task. In the other case, in the other two, you have the dimensional estimation of the smallest object. So you can, this I think is done via classical approach. So you count the number of pixels of the snack, and the last one is a classification, also in this case, but the result is a malformed snack.
And this is small, by the way, in Italian, because you reading that.
Piccola is small.
Okay.
Okay, and another case, you also say always on snacks, on the same snack, was to detect where the anomaly was. In this case, the idea was to use a GAN, so a generative adversarial network, to having an half of the snack to generate the corresponding half, and then see if there was then how can I say? You take the snack, you split the snack in two. You give to the GAN as input the half that you extracted. The GAN generates the other half, the second half, and then you can do a subtraction, comparison pixel by pixel, and you see where the defect is. In this case, for example, the first image on the left is the sample. The second one, as you can see, there's a line in the middle. So here is where the snack was cut in half, and then the lower part of the snack was passed to the GAN to generate the higher end of the snack, and then the first snack was subtracted to the second snack to obtain the result in the third one, where the anomaly is circled in green. Okay. This is the last. In this case, some kind of problems where you can't have the samples, the defective samples. You can try to train the networks only on good samples. So the idea is to train a network to detect anomalies. So in this case, the anomaly detection goal was to detect I don't know, screws or something like that on this trail. So the train image, the train dataset was composed by images like this one, and the inference images. The inference images are like this one. So on the left, the task was to detect if there were some screws on the trail, while on the right we need to have an estimate of a percentage of the fullness of the trail. So the result is something like this, where you have an heat map where the image given in input differs from the images that the neural network has seen in training. So on the left, you see that the screw is highlighted in red. So you have the area where there is the anomaly. And on the right, you have a more complex heat map, where for each square, for each rectangle, you have the coverage in percentile of the screws on the trail, and the complexity, the total percentage of the coverage on the trail is given by the mean of all these values. And this is an approach where you can, it's not anomaly detection in terms of, it's not strictly anomaly detection, but is an approach that you can use for these kind of tasks.
Okay, so let's wrap up with a quote from Stephen Hawking. I'm confident that each of you has successfully deciphered this peculiarly constructed sentence. Intelligence is the ability to adapt to change. If you feed this image to ChatGPT, it will probably surprise you by flawlessly reading the quote. This demonstrates how AI has entered our world and continue to shape it, including the realm of non-destructive inspection. So this concludes our presentation, and thank you everyone for participating and listening to us. And feel free to ask any question. We will answer to them.
Thank you, Matteo and Mattia. I don't know if within the audience there is any question, any doubt you want to be solved.
So I'll also put the context if you want to ask us later.
Yeah, well, maybe one question from my side.
Yeah.
I guess in let's say a successful project or artificial vision project, in order to be totally successful, is a kind of combination between the hardware, the cameras, the processing, and probably the training, the inference, and so on. I don't know, is there any of those components really more important than others, or what is the actual combination between them? Or at least how would you balance? I don't know, it's a tricky question.
Yes, it's a tricky question, but is a good question. Thank you. And I think the most important thing is to try to feed the network with or white or black images. So you can't put something uncertain in the model, because the model will respond you with different answers, and the answers can be random or can be very uninterpretable. So I think the better the images you feed to the network, the better the answer the network will give. Then there is the training process. So you have to split it very well, the data set, and you can't feed, for example, 1,000 images of a good sample and 1 image only of a defect. This can fail every model you will train with it. So you have to select carefully the data you are feeding to the model. So if you have good data on the beginning, you can choose from the data the better images, the best images. If you have bad data, you have to carefully select it to the learning process, I think.
Okay, thank you. There are a couple of questions in the chat. Let's start with the first one from Alfredo from Factor. What about the measurement? You said there, your presentation in anomaly data detection, but in ZDZW, you have been developing measuring capacities. At which level of precision?
It depends very much on the camera used, because you have a 20 megapixel camera, you can see, you can zoom in on the piece and have the desired dimensional accuracy. There is a limitation also. The camera can be put in tight environments, so you can't have the focus the camera needs to have a high resolution, or the illumination required for have a nice resolution. So you must balance the application requirements with your capabilities on putting everything inside a box that analyzes the samples in the production line, I think. So it is very dependent on the industrial side, and a solution can be not always found because of the limitation of the factory, the plant, or the tightness of the system, or the absence of relevant hardware to analyze the smallest dimension. So I think I can answer that question with this consideration.
Thank you. Let's continue with Pablo from Mira. What are the usual percentages you use for each training database?
It also depends very much on the application. I think on 70%, 15-15 is a good guess. But if you have a lot of data, you can also try to generalize it with a 50, 25, 25 if you have really a lot of data. If you have a small number of images, but I mean 1,000 images, the minimum required, or 500 minimum 500 images, you can try to push the model with 80, 10%, because but you will have problems in generalization, because you can't probably evaluate all the types of images a model can see. So the validation could be limited in the metrics evaluation, and the test will be biased to the images you have selected for the task of the testing phase. I think that answered the question.
Okay, another one from Javier from GPP. What tools can be used to improve algorithm performance when it comes to creating new data based on data augmentation? Also, any tools recommended when tuning in hyperparameters?
Okay.
Okay, my question.
It's your question. If you.
Okay, so creating new data is not simple. So data augmentation generally refers to augment the data that you already have. So I mean, it's the transformation that you do on each epoch when before feeding the images to the neural network, and these transformations are I mean standard, so you don't have too much improvement by this side. If you want to if you mean otherwise to generate new data synthetically, it's difficult. It's difficult to have networks that done this. It's difficult to have the hardware to do this. There are some solutions. I mean, for example, also NVIDIA with the suite of NVIDIA, the NVIDIA Omniverse can be used to generate images or also three-dimensional data, three-dimensional scenarios, three-dimensional point clouds, and data like this, because you have neural networks that work only on images, or neural networks that work only on I mean spatial information, like distance or like depth. There's a lot of tools. Basically, the ones that provide NVIDIA are the best ones. Regarding the hyperparameter tuning, there are some Python libraries. I think something like it is called Optuna. I think
also there is a Guild package, the Guild library, but I think it's a beta. But I've used it.
There are some tools. Some I mean some approaches, some neural networks, some repositories give you the possibility to perform hyperparameter optimization during a simple training. So what this means? It means that the training process starts with a set of different trainings, starting with the same initial data set, where every neural network, every training is started with a different set of different mapping hyperparameters values. So the system is able to maintain only the experiments that perform better. So if you start with, I don't know, three experiments, and see that the first experiment after 10 epochs have an accuracy of I don't know, 70%, and the second one has an accuracy of 80%. The first one is killed, and also the second one is maintained. So these are the tools that can help you in performing this kind of hyperparameterization tuning. But also in this case, it's a heavy task. It's a computational heavy task, because you have to have the hardware to do this. Maybe a cluster or something like that, because you have to perform trainings in parallel. So you have the
time or hardware or
time, yeah,
or a lot of time.
It depends on the requirement, because you have to generate, well, you have to have the models in parallel, and you have the different instances of data set in parallel. So you have to also to have an infrastructure, an hardware infrastructure that allows you to do this. But there are some tools. Optuna, always NVIDIA has this kind of tools. So there are some of them. You can also implement it by hand, but it's not advisable. It's advisable for teaching purposes, but it's complicated.
Production.
It's incredibly complicated.
Thank
Okay.
you. Is there any final question before we close the webinar? Okay, well, if not, if not, give you a big thank you for the nice presentation today. Well, as a small reminder, here in the last slide, you have the contact of our colleagues from the system, Matteo, Mattia, and Mauro. Don't hesitate to contact them if needed to solve any doubt around artificial vision, well, analysis and implementation. Of course, don't forget to follow the ZDZW project for additional info. And apart from that, we'll be uploading this webinar in case you want to rewatch it in a few days in our YouTube channel. Apart from that, a big thank you for being with us today, and we will be in contact. Thank you.
Thank you all for the contribution and questions. Have a good day, everyone.